From H.G. Wells' groundbreaking novel The Time Machine to the countless science fiction films and books that followed, the concept of time travel has captivated humanity for generations. The idea of venturing into the past to witness historical events, or leaping into the future to glimpse what lies ahead, holds an enduring allure. This fascination stems from our intrinsic curiosity about time itself, a fundamental dimension of our existence. We are bound by its relentless forward march. Yet the dream of manipulating time, of breaking free from its linear grip, remains a powerful driver of imagination and scientific inquiry. Time travel, if achievable, would revolutionize our understanding of the universe and our place within it. It could potentially allow us to correct past mistakes, avert future disasters, or simply satisfy our insatiable thirst for knowledge. The implications are staggering, touching upon everything from personal relationships to the very fabric of reality. But is time travel truly possible, or is it destined to remain forever confined to the realm of science fiction? Let us embark on a journey through the latest scientific discoveries to explore this captivating question. Albert Einstein's theory of relativity, published in the early 20th century, revolutionized our understanding of space, time, and gravity. It introduced the concept of spacetime, a four-dimensional framework that unifies space and time into a single entity. One of the key implications of relativity is that time is not absolute as previously believed, but rather relative. The rate at which time passes can vary depending on the observer's relative motion and the strength of the gravitational field they experience. This phenomenon, known as time dilation, is a cornerstone of relativity.
It predicts that time slows down for objects moving at high speeds relative to a stationary observer. The faster the object moves, the slower time passes for it. This effect has been experimentally verified numerous times, most famously with atomic clocks flown on high-speed jets. The clocks on the jets, upon landing, showed a slight time lag compared to clocks that remained stationary on Earth, confirming Einstein's predictions.
Another aspect of time dilation arises from the influence of gravity. According to general relativity, time slows down in stronger gravitational fields. This means that time passes slightly slower at sea level than on a mountaintop, where the gravitational pull is weaker. While these differences are minuscule in everyday life, they become significant in extreme environments such as near black holes, where gravity is incredibly strong.
The concept of time dilation has profound implications for the possibility of time travel. It suggests that by manipulating speed or gravity, we might be able to influence the passage of time and potentially travel to the future. While traveling to the past presents more formidable challenges and remains largely theoretical, the idea of venturing into the future, thanks to Einstein's insights, has moved from the realm of pure fantasy into the realm of scientific possibility.
The concept of time dilation offers a tantalizing glimpse into the potential for future time travel. As Einstein's theory predicts, time slows down for objects moving at high speeds relative to a stationary observer. This means that if a spacecraft could achieve velocities approaching the speed of light, time would pass much slower for the astronauts on board compared to people on Earth. Upon returning to Earth, the astronauts would have effectively traveled into the future, as more time would have elapsed on Earth than for them during their high-speed journey. Consider a hypothetical scenario. A spacecraft travels at 99% the speed of light to a star system 10 light-years away. From the perspective of Earthbound observers, the journey would take just over 10 years. However, for the astronauts on board, time dilation would significantly slow down the passage of time. For them, the journey might only take a few months or even weeks.
Upon returning to Earth, they would have aged significantly less than their counterparts who remained behind, effectively experiencing a leap into the future. While achieving such high speeds presents immense technological challenges, the principle of time dilation remains a fundamental aspect of our understanding of the universe. Even at the speeds currently achievable by spacecraft, time dilation effects, albeit minuscule, are measurable.
As technology advances, the prospect of utilizing high-speed travel for journeys further into the future becomes increasingly plausible, albeit still a distant prospect. The concept of traveling to the future through high-speed travel, while theoretically sound, faces significant practical hurdles. The energy requirements to accelerate a spacecraft to near-light speeds are astronomical. Furthermore, the effects of prolonged exposure to high acceleration and cosmic radiation on human physiology pose serious challenges.
Nevertheless, the idea remains a captivating possibility, a testament to the power of Einstein's revolutionary insights into the nature of time. While traveling to the future through time, dilation seems scientifically plausible, albeit challenging. The prospect of traveling to the past presents more formidable obstacles. One of the most intriguing theoretical concepts for backward time travel involves wormholes, hypothetical tunnels that connect different points in spacetime. These theoretical constructs, predicted by Einstein's equations, could potentially create shortcuts through the fabric of spacetime, allowing for travel between distant regions of the universe and perhaps even different points in time.
Another concept related to backward time travel is that of closed time-like curves, or CTCs. These are paths through spacetime that loop back on themselves, potentially allowing an object to return to its own past. While the existence of CTCs is not explicitly forbidden by Einstein's theory of general relativity, their existence raises profound questions about causality and the consistency of the laws of physics.
The existence of wormholes and CTCs remains highly speculative, with no observational evidence to support their existence. Moreover, even if they do exist, the stability of wormholes and the possibility of traversing them remain open questions. Some theories suggest that wormholes might be inherently unstable, collapsing rapidly upon formation, while others propose mechanisms for stabilizing them, perhaps through exotic forms of matter with negative energy density.
Despite the lack of concrete evidence and the formidable theoretical challenges, the concepts of wormholes and CTCs continue to fuel scientific inquiry and inspire countless science fiction narratives. They represent tantalizing possibilities, pushing the boundaries of our understanding of spacetime and challenging us to grapple with the mind-bending implications of backward time travel.
Paradoxes of time. The grandfather's dilemma. One of the most perplexing aspects of time travel, particularly backward time travel, is the potential for paradoxes. These are logical inconsistencies that arise when considering the possibility of altering the past.
Perhaps the most famous example is the grandfather paradox. Imagine a time traveler venturing into the past and accidentally killing their own grandfather before their father was conceived. This action would create a paradox, as the time traveler's own existence would become impossible, yet they already exist to have traveled back in time.
The grandfather paradox highlights the potential contradictions that arise when considering the possibility of changing the past. If the past can be altered, it raises questions about the consistency and stability of the timeline. Does altering the past create a new branching timeline, or does it somehow erase the original timeline, leading to paradoxes? These are questions that have puzzled physicists and philosophers for decades.
Several attempts have been made to resolve the grandfather paradox and other time travel paradoxes. One approach is the Novikov self-consistency principle, which suggests that the laws of physics somehow conspire to prevent paradoxes from occurring. This principle proposes that any attempt to alter the past will ultimately fail, or will result in events that are consistent with the present.
Another approach involves the many worlds interpretation of quantum mechanics. This interpretation suggests that every quantum measurement causes the universe to split into multiple parallel universes, each representing a different outcome of the measurement. In the context of time travel, this could mean that altering the past simply creates a new branch of the universe, leaving the original timeline intact.
While these are intriguing possibilities, the resolution of time travel paradoxes remains an open question.
Quantum quirks, time's uncertain nature. Quantum physics, the branch of physics that governs the behavior of matter at the atomic and subatomic levels, introduces further complexities into the discussion of time travel.
One of the key principles of quantum mechanics is the uncertainty principle, which states that certain pairs of physical properties such as position and momentum cannot be simultaneously measured with perfect accuracy. This inherent uncertainty in the quantum realm has led some physicists to speculate about the possibility of quantum fluctuations in space-time, potentially opening up avenues for manipulating time at the quantum level. Quantum entanglement, another bizarre phenomenon in quantum mechanics, involves the interconnectedness of two or more particles, regardless of the distance separating them. A change in the state of one entangled particle instantaneously affects the state of the other, even if they are light years apart. This seemingly faster-than-light connection has led some to speculate about its potential implications for time travel, although no concrete mechanisms have been proposed. Another intriguing concept in quantum physics is quantum tunneling, a phenomenon where particles can pass through energy barriers that would classically be insurmountable. This phenomenon has led some to speculate about the possibility of tunneling through time, although the theoretical framework for such a process remains highly speculative. The intersection of quantum physics and time travel remains a fertile ground for theoretical exploration. While the implications of quantum mechanics for time travel are still largely unknown, the strange and counterintuitive nature of the quantum world suggests that our understanding of time may be far from complete. Perhaps hidden within the quantum realm lie the keys to unlocking the secrets of time travel. Particle physics and time secrets. Particle physics, the study of the fundamental building blocks of matter, also offers intriguing avenues for exploring the nature of time. Experiments conducted at particle accelerators, such as the Large Hadron Collider, allow scientists to probe the behavior of particles at extremely high energies, mimicking conditions that existed shortly after the Big Bang. These experiments provide valuable insights into the fundamental laws of nature and could potentially reveal new information about the nature of time. One of the key goals of particle physics research is to unify the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces. A unified theory of physics could potentially shed light on the nature of space-time and the relationship between space and time, offering new perspectives on the possibility of time travel. The search for new particles, such as hypothetical tachyons, particles that travel faster than light, also holds potential implications for time travel. While the existence of tachyons remains speculative, their theoretical properties have led to discussions about their potential role in transmitting information faster than light and potentially influencing the past. The ongoing research in particle physics continues to push the boundaries of our understanding of the universe. While no definitive answers regarding time travel have emerged, the discoveries made at particle accelerators and the theoretical frameworks developed by particle physicists provide valuable clues in the quest to unravel the mysteries of time.
Section 8. Simulating Time, Virtual Voyages. While physically traveling through time remains beyond our current capabilities, scientists are exploring the possibility of simulating time travel through computer models and virtual reality environments.
These simulations allow researchers to explore the theoretical implications of time travel without the constraints of physical limitations.
By creating virtual universes with different time travel scenarios, scientists can test the consistency of physical laws and explore the potential paradoxes that might arise.
Virtual reality technology offers another avenue for exploring time travel.
By creating immersive virtual environments that simulate different time periods, researchers can study the psychological and cognitive effects of experiencing different timelines.
These virtual time travel experiences could provide valuable insights into how humans perceive and interact with time.
Computer simulations and virtual reality environments also offer valuable tools for educational purposes.
By creating interactive simulations of time travel scenarios, students can explore the complex concepts of relativity and quantum mechanics in an engaging and accessible way.
These virtual experiences can enhance understanding of the scientific principles underlying time travel and foster critical thinking about its implications.
While virtual time travel cannot replicate the physical experience of actually traversing time, it provides a valuable platform for exploring the theoretical and philosophical aspects of time travel.
As technology advances, these simulations and virtual environments will become increasingly sophisticated, offering ever more realistic and insightful glimpses into the potential of time travel.
Time travel's horizon, current status, and future dreams. The dream of time travel, while still firmly rooted in science fiction, continues to inspire scientific inquiry and fuel our imagination. While physically traveling through time remains beyond our current technological capabilities, the theoretical frameworks developed by physicists, particularly Einstein's theory of relativity and the intriguing possibilities of quantum mechanics, offer tantalizing glimpses into the potential for manipulating time.
The ongoing research in particle physics, the exploration of wormholes and CTCs, and the development of sophisticated computer simulations are all contributing to our understanding of the nature of time and the possibilities of time travel.
While no definitive answers have emerged, the quest to unravel the mysteries of time remains a driving force in scientific exploration.
The ethical and philosophical implications of time travel also warrant careful consideration.
If time travel were to become a reality, it would raise profound questions about our responsibility to the past and the future.
The potential for altering history, creating paradoxes, or inadvertently disrupting the delicate balance of the universe would require careful ethical guidelines and regulations.
While the prospect of stepping into a time machine and venturing into the past or future remains a distant dream, the pursuit of understanding time travel continues to push the boundaries of human knowledge and inspire us to contemplate the vastness and complexity of the universe.
Perhaps one day the dream of time travel will become a reality, opening up new frontiers of exploration and understanding.